just like write itself and then do that? Yeah.
Morning. We've got some ground to cover today. I think it's going to work out nicely. Wrapping up the very end of chapter 12, and we're going to start on the kind of the only major topic from chapter 13 that we're talking about in this class today. So we're getting into the final sort of. After today, there should be really only one more topic that we're going to cover, and that's and we'll do that at the first half of Monday, and I'm trying to leave the second half of next week for kind of example problems. So if I'm rushing through some of this stuff without as many examples as I would usually do, please bear with me. I'm trying to get the material across so that you have the stuff down to do the homework in a timely manner, and we'll work on applications at the very end. So, all right, 3 questions up here to kind of prompt some recall from last time and segue into the last stuff from chapter 12. So, all right, we've got these curves here, an A and a B, that describe the spectral emissive power for a black body, right? We know it's a black body because this E sub lambda up here also has a B attached to it, which means it's an ideal emitter. So here's sort of the gimme, right? Between A and B, which one corresponds to radiation from a black body at a higher temperature? A, right? Easy to tell. 2 ways is that the curve is higher everywhere. Okay, so you have higher emissive power at every wavelength for a higher temperature black body. The other way you can tell is because the peak here moves down the wavelength axis as the temperature increases. So the wavelengths of emission get shorter as the temperature goes up. So those are the 2 sort of important features of black body radiation curves. Okay. What do we call the area underneath this curve? So if this curve is the spectral emissive power, let's say we anyone recall this little vocabulary quiz? Let's give you 3 choices. Emissive power, emissive intensity, or black body hemispherical intensity. Okay. I made that last one up, so, sort of. Anyway, among those 3, any ring a bell? Emissive power, right. So we have a spectra. That spectral describes as the variation with wavelength. If we integrate under the wavelength, it's the emissive power, also sometimes called the total emissive power. So if that helps you remember it, total, okay? And the beauty of this is, right, we already have the equation from like the very first or second lecture, right, that describes the area under this curve. Anybody remember what that equation is called? Or is it? It's a heat rate, or sorry, a rate equation that we introduced right at the beginning of the class. In this case, we're looking for E equals something. When we introduced it at the beginning of the class, it was Q radiation equals something. Or Q, sorry, prime. If we went ahead and, right, so these curves are described by, remember there's this equation called the Planck distribution. I'm not going to write it again, but it was this sort of nasty function of both lambda and temperature. All right. And if we integrate it across lambda, the area under that curve would end up being this guy right here. Sigma times t to the fourth. Okay, does this look familiar? Known as the Stefan Boltzmann Law. Where sigma is equal to 5.67 times 10 to the negative 8th watts per meter squared, Kelvin to the fourth, which is creatively known as the Stefan Boltzmann constant. Okay, so this is good, right? This means that we had these pain in the butt equations that described the variation with emissive power as a function of wavelength, but if all we're interested in is the total emissive power, right, E, which is in the form, a familiar form of a heat flux, then all we need to know is the temperature. And this also shows sort of the same behavior we're seeing up here where, right, temperature goes up, so does the area under the associated curve. Okay? The only twist I'm going to add to this is that black bodies, one of the characteristics I introduced is that they are what are known as diffuse emitters. Remember, that means that they emit radiation in all directions without any bias. They're omnidirectional. And so because of that, if we wanted to express the radiation intensity of a black body, okay, in this case this would be the total radiation intensity, so basically integrating across all the wavelengths. So it's saying, the amount of energy being cast out in a particular direction, regardless or cumulatively across all wavelengths. This would be simply this E value of the black body, should put a sub B there, divided by pi. Okay. And this is the total emissive intensity. And you might only want to know this because it tells you, again, sort of the concentration of that emission across solid angles. So, okay. So here is where we started. That was the black body, right? The black body, the perfect ideal emitter. What we want to talk about now is how real surfaces, that's a terrible A, real surfaces behave. And by real surfaces, I mean anything that is, not this idealized mathematical abstraction. So we've covered part of this already. So this should just be sort of firming up some definitions we've already talked about. The idea is this. If you have a real surface, you can write its spectral emissive intensity, E lambda, which is a function of lambda, equal to the spectral emissivity, which is a function of lambda, times the spectral emissive power of a black body. And so this essentially becomes the spectral emissivity times your Planck distribution, or those curves that we drew right at the beginning of the lecture. Okay. So graphically, what this would look like is, say we've got our nice ideal black body radiation. And so this is our Planck distribution right here. Let's put here lambda and E lambda. And then our real surface, whatever that surface is, something that's made of metal or wood or glass or what have you, some physical surface, might have a spectral emissive power that looks more like this. Okay? So the idea is that at every wavelength, this spectral emissivity is the ratio of the real surface to the ideal black body. Okay? We have an equation that describes the black body, and if we know the spectral emissivity, that epsilon sub lambda, then we can recreate this. Okay? If we're interested in generally heat fluxes, okay, this is going to come back to a familiar expression again. Then we're interested in the ratio of the area under these respective curves. Okay, so let me kind of retrace that. So if we integrated under both of these curves and took the ratio of those, we would end up with what's known as the total emissivity, which is the thing we introduced once again early on in the class, this idea of emissivity. So the integral from 0 to infinity of epsilon lambda E lambda B lambda over lambda B d lambda, which just works out to be E over EB. Okay. So there's our definition of emissivity and our notional expression of what the spectral emissivity is. Okay. So, very important fact here, and if you leave this room with nothing else from this lecture, I want you to remember this, that both epsilon and epsilon sub lambda are always going to be less than or equal to 1. The only time they're equal to 1 is if the thing we're talking about is actually a black body. There are some surfaces that behave like black bodies pretty well. Okay, celestial bodies, the sun, etc., are pretty good about this. But for any real surface, you hit a cap right here, which goes hand in hand with that, what I was saying before, that a black body is the perfect emitter. So all this is saying is graphically, this blue curve can never go above the red curve, and the area under the blue curve can never exceed the area under the red curve. So it's trivial, but the idea is that that this expression right here leads to the familiar expression for the emissive power of a real surface, which is that E equals epsilon times E sub B, or epsilon sigma T to the 4th. And so we'll go ahead and say this is the emissive power, or total emissive power, of a real surface. Okay, absorptivity. So that's emissivity, right? The other side of this coin is absorptivity. And absorptivity has the exact same sort of behavior, right? The idea is a black body is also considered the perfect absorber. It absorbs 100% of all radiation that is incident upon it, meaning that none is reflected and none is transmitted. So rather than drawing the absorptivity spectrum, right, and redoing that whole process, I'll trust that you guys can generalize the same idea. And let me write alpha is equal to, right, the integral of the spectral absorptivity times the spectral irradiation. Okay. So again, if we're talking about this graphically, this would be the area under the curve that tells us how much of all of the incident radiation actually gets sucked up by the body it's hitting. And this is the total of all of that incident radiation. Again, as with emissivity, the idea is that alpha and alpha lambda both have to be less than or equal to 1. And from this, we can calculate the the amount of absorbed irradiation using the also familiar expression of alpha times G. Absorbed irradiation of a real surface. Okay. So we've got emissivity, we've got absorptivity. Remember when I was starting out talking about radiation, I said there were two others. There's reflectivity and transmissivity. We're going to make a pretty bold but useful assumption here that for the remainder of our whole next week, and in general, most of the heat transfer problems you're going to encounter as an engineer, we're going to assume that the transmissivity of our objects is equal to 0. That is, that all of the surfaces we're considering are opaque to radiation. And then from this, the idea is now that the reflectivity rho is going to be equal to 1 minus lambda and rho, or 1 minus alpha, and rho lambda is going to be 1 minus alpha lambda. Okay. We're able to do this because, remember, tau plus rho plus alpha has to equal 1. The sum of the absorbed, the reflected, and the transmitted radiation has to always be the total radiation that's hitting an object. And so by setting this guy equal to 0, this means we have just rho plus alpha have to equal 1, and rho sub lambda plus alpha sub lambda have to equal 1. So this gives us now the total reflectivity and spectral reflectivity. Okay. One more note on real surfaces. We talked about what a diffuse emitter is, okay, something that emits radiation uniformly in all directions. We talked about what diffuse irradiation is, right? Incoming radiation that's coming in uniformly from all directions. And I want to talk here about, so that takes care of, right, G. We know that G is uniform in all directions. We know that E is uniform in all directions. But the other type of radiation that's going somewhere is reflected radiation. And so I want to specify what a diffuse reflector is. And this is a pretty natural extension, the idea of a diffuse emitter. If we have a surface and it's got some radiation incident upon it, right? We'll say here's G, and of course, some of that is going to go into the surface, and that's going to be alpha G, and some of it is going to go out of the surface, and that's going to be the reflected radiation. But if we assume it's a diffuse reflector, then that reflected radiation is going to be scattered back in all directions. Okay. And so this would be rho G. Okay. The advantage here is that if G is coming in uniformly from all directions, if it's actively emitting uniformly in all directions, and if any incident radiation is reflected uniformly in all directions, then all of the radiation that's shooting around can be considered uniform in all directions, which makes analysis much, much simpler when we start talking about multiple surfaces next to one another. And that wraps up the definitions for real surfaces. Okay, so before I describe what a gray surface technically is, any questions on what we just put up here? Okay. So gray surfaces are something we mentioned previously. All right. Also, in Chapter 1, we're going to firm up that definition so that we know the assumptions by which we're limited when we're talking about certain types of problems. So hopefully it's become apparent at this point that radiation, it's 99% bookkeeping. Okay, it's figuring out what alpha is, it's figuring out what epsilon is, and figuring out what your various spectral and total emissivity and irradiation quantities are, and just adding them up in different ways. This is made a lot easier if we can make one assumption, and that is that alpha equals epsilon. Okay, that the absorptivity is equal to the emissivity. Problem is that this applies, not apples, applies, only under a certain set of assumptions. Oh, good. Okay, alpha epsilon applies only under certain conditions. And there's a whole section of the book dedicated to deriving what's known as Kirchoff's law. And from that going into gray surfaces, we're going to skip that because most of it is sort of just going to show what isn't useful. The takeaways from that section, though, are that if we can say that irradiation is diffuse, that the surface is diffuse, And what I mean by that is that the emissivity, the absorptivity, and the reflectivity are all directionally independent. And the surface is what's known as gray, which means that alpha lambda and epsilon lambda are independent of lambda. Okay. So broad strokes are that through a kind of manipulation of some theory, numbers 1 and 2 combine to give us one sort of thing. If numbers 1 and 2 are satisfied, then we can say that alpha lambda is equal to epsilon lambda. All right? So satisfying 1 and 2 means that our two spectra are going to look the same. So that what we have to do is say, do those spectra, are they basically just flat lines, uniform, right, across all wavelengths? So if shown that the spectral emissivity and absorptivity look like flat lines. If we satisfy 1, 2, 3, then we can make that very helpful assumption that alpha equals epsilon. So, a couple of quick little comprehension checks here. Let's say we've got spectral lambda and lambda. Spectral emissivities and absorptivities that look like this. Does this satisfy points 1, 2, and 3? Just hands up for yes. Hands up for no. Okay. This satisfies point number 3. But if we look at points 1 and 2, like we don't know whether they're diffuse. We don't know, but we can say that, right, numbers 1 and 2 together state that alpha sub lambda and epsilon sub lambda should be equal. These aren't equal. Okay, so the idea is that it violates rules 1 and 2. Okay. What about this guy? Again, we'll assume that red is alpha and blue is epsilon. Yes, hands up for yeah, good to go. Hands up for no, that does not satisfy the rules. Okay, we're getting a little less, fewer sure answers here. Okay, rules 1 and 2. If we stop worrying about them individually and worry about kind of the combined thing, sure, alpha sub lambda and epsilon sub lambda are equal. Those curves lie right on top of each other. But rule 3, they are not independent of lambda, right? They're not uniform along the lambda axis. So in this case, we cannot say that alpha is equal to epsilon, or that the total emissivity and total absorptivity are equal, because if violates, right, number 3. And so for both of these cases, we cannot say that alpha is equal to epsilon. We're basically, that assumption can't be drawn, or conclusion cannot be drawn. And what about this guy? There's hands up for yes. There we go. Hands up for no. All right, bingo. This guy satisfies all the requirements and that the curves lie on top of each other and they do not vary with lambda. So this satisfies the results, and we can say that alpha and epsilon are equal to one another. And all right, let's throw a little bit of a twist in here. This is sort of this is going to be a more realistic situation. Okay, let's say we've got something that looks like this. I guess hands up for yes, hands up for no, hands up for it depends. There you go, observant. So a situation like this, technically, no, it does not satisfy rules 1, 2, and 3. Okay, because we see that sure 1 and 2 are satisfied, and that alpha and epsilon, the spectral distributions, are on top of each other, but right, it's not independent of lambda. However, we've got a pretty flat stretch right here. And so if we consider the spectral emissive power and spectral irradiation that we're like concerned with in this particular problem, then we might be able to get away with ignoring these spots where it varies with wavelength. What I mean by that is, so here we have alpha and epsilon. Let's draw the spectral emissive power and spectral irradiation right beneath it. Let's say we have this guy is our black body radiation at the temperature of interest. Oops. And say our spectral irradiation looks like this. Okay. The idea here is that if we say, okay, look, when do the absorptivity and emissivity matter? They matter in how they modify the black body spectral emissive power and the total spectral irradiation. And so if those sort of the outgoing and the incoming radiation are limited in terms of the wavelengths that they occupy, and if in that range of wavelengths our alpha and epsilon are pretty flat, then this is a case when we can realistically say we can approximate this thing as a gray surface. Okay, so this is a rule of thumb. Is look at G and your black body radiation for the temperature being considered, and see whether they're limited to a band where you can basically just draw a horizontal line through your alpha and epsilon spectra. If, on the other hand, let's say our black body radiation wasn't out there, but it was out here, it's a no-go, because now we have black body spectral emissive power concentrated in an area where it violates rule number 3. Okay. But if in fact it sticks to that region, then we can say alpha equals epsilon as long as B and G are what are known as band limited to wavelengths where okay. So this overwhelmingly, again, in anything we do in this class and anything you do at this level of heat transfer, you're almost always going to get to make this assumption. But it's important that you understand when you can't. So hopefully that. Are there any questions that crop up after that? So we just plowed through the end of chapter 12 right there. We're done with the vocabulary and background and sort of the minutia of spectra and total and hemispherical what's-its. What we're ready to start getting into now is how we actually use this for radiation, heat exchange between surfaces. Okay, so the entire last week plus has been spent on, like I said, just considering the spectral emissions and the total emissions and the irradiation on a single surface, more or less. Okay, and the reason for that, the reason it's important, is because we need to understand, like, that's the easiest way to introduce with any technical rigor what the different radiation quantities actually mean. But the reason we're here, right? The reason this class is called heat transfer is because we're interested in knowing what this radiation, like what the heck does this have to do with how much a plate over here is going to get heated up by a plate over here. Okay. So the idea is, right, irradiation has to come from somewhere, and any emitted radiation has to go somewhere. So anytime you have surfaces that are near each other, or not even near each other, anytime you have surfaces that are within view of one another, there's going to be some transfer of thermal energy between them through the action of radiosity or emission and irradiation. So our main tool here is going to be something that we call the view factor. And I introduced this in one of our previous examples, so hopefully this rings a little bit of a bell. But thankfully, this is one of the most intuitive tools in heat transfer. So the view factor, which is also known as, in some other books and in some other classes, the configuration or shape factor. So the idea is this. Let's say you've got a surface here. Let's make these actually round. You've got a surface here and a surface here. We'll call this guy A. We'll call this guy. No, actually, let's call this guy I and J. I and J. All right. I is going to be sending out actively emitting radiation. Here's its total emissive power, and thrown out into the ether. And some of that is going to hit J, right? Some of what hits J will be absorbed, and some will be cast back towards I. Similarly, J is going to be radiating energy, some of which will hit I and go in, and some of which will be reflected back out of I. And remember that, so if we assume that everything here that's going on is diffuse, in other words, these are diffuse emitters, meaning each one of these arrows should really be a collection of arrows going in all directions. And any reflected radiation is also going to be going in all directions. Then the idea is we've got some active emission as well as some radiation bouncing back and forth in between. So the total radiation that's coming out of I, okay, this is going to be going back to the very first discussion of radiation week before last. We could say that the total, I guess, amount of radiation flux from I, right, would be what's being actively emitted plus what's being reflected, like the stuff from J that's being reflected back out. Okay. If you remember, we call this the radiosity, the sum of all outgoing radiation from an object. Okay. And so if we want to know the total rate, so this is the flux. If we want to know the total rate of outgoing radiation, we would say that J times, so Ji times AI, that is the surface area, would give us Q of I kind of out into the world. Okay. Everyone with me here? Similarly, JJ. Someone needs some nasal spray. So J sub J times A sub J would be, the radiation that's heading out from J outward. So I want to be clear here that this is, right, all this is doing is it's saying there's what's being actively emitted and there's what's being reflected, and together those two constitute all of the outgoing radiation. Okay. The view factor is defined very simply as this. If we say F, I, J, then what this gives us is the total amount of energy being transferred from I to J divided by so this would be Q I to J over Q I out. Okay, it's the fraction of all of the outgoing radiation that ends up hitting object J. Right? So this is actually a pretty intuitive concept. And you can also hopefully see how useful this is immediately. If we know F, and the beauty is there's a bunch of tables put together that have values of F pre-compiled for common geometric configurations. If you know F and you know J in the surface area of something, then you can immediately figure out how much of that radiated energy finds its way, that becomes incident on another object. All right. Timing here is pretty perfect, actually. So if you remember that example we did, I'm trying to remember, I think it was either the beginning of this week or end of last week, right, where we had an emitter, a diffuse emitter, A1, and we had a receiver, A2. Okay. Remember the way we figured out the total amount of radiation from A1 that hit A2? We did it two ways. The first was to actually set up the radiation intensity, integrate it over the solid angle, and then figure out, doing a bunch of integrals. The other way we did it was we said, if A1 is truly diffuse, then it's emitting radiation uniformly across the entire hemisphere that's visible from the top of this surface. And then we figured out here was the angle subtended by A2, and essentially how much of this hemisphere is taken up by the projected view of A2. And so we ended up saying that Q from 1 to 2 was equal to Q of 1 to this hemisphere times the angle subtended by 2 over the angle subtended by the hemisphere, which ended up being I don't remember the numbers off the top of my head. But anyway, and so what we've got here is basically so this is sort of the Q out, right? If the hemisphere is the entire accounts for all of the radiation that's being cast out by surface 1, we go ahead and rewrite this as out, Q1 total. Then what we've done basically is if we rearranged this and wrote Q12 over Q1 out, omega 2 over omega hemisphere, then what we did is for this problem we calculated the view factor from 1 to 2. That's sort of written off there in the corner. This is so we've already actually done some of this. I want to be clear though that this is not always the way to do it, because there are some situations in which the arrangement of different geometries, it might not be simple enough that you can just calculate subtended angles. But for a problem like this, where you've got one object and another one at some point, you say, well, clearly this thing can send radiation out to the entire hemisphere. How much of it ends up hitting this thing? And there's a very simple way to approximate the view factor right off the bat. So what I'm going to do is I'm going to get started on their view factors in general are governed by kind of 2, if you look at the book, but really 4 kind of rules that make it easier for us to actually calculate view factors from values that we already know. So I'm going to give you the first 1 or 2, and then we'll resume. Rules for view factors. Okay. First off is what's known as the Reciprocity Rule. And this says that AI times Fij is equal to AJ Fji. If you want to picture this like graphically, what this means essentially is that if you were to figure out the fraction of radiation from object I that's hitting object J, right? Those occur in rays, the transmission of electromagnetic waves. If you were to trace backwards along those rays, you would end up hitting object I. Okay. So if we have the view factor for one object, okay, from I to J, and we happen to know the surface areas of both of those objects, then it's very easy to figure out what the view factor going the other direction is. This one's key for the homework. Number 2, and we'll go ahead and end it here, is what's known as the Summation Rule. So numbers 1 and 2, the Reciprocity and Summation Rule, are the 2 most important. Numbers 3 and 4 kind of follow along from this, but we'll introduce those on Monday. The Summation Rule applies to enclosed spaces. Applies to enclosures. So let's say we've got an object like this, basically we say it's the radiation is occurring on the inside of this enclosure, and we've got 1, 2, 3, 4. So 4 surfaces making up this enclosure. It can be any number of surfaces, though. What the summation rule says is that the summation from j equals n of fi to j has to equal 1. In words, this means that if you pick an I, let's say we pick surface 3, then all the radiation out from 3 has to hit 1, 2, 4, or back on itself. Okay. So when it's in an enclosure, all the radiation coming out from one surface has to hit something. So this fraction of how much radiation hits something has to cumulatively add up to 1. And with that, we'll go ahead and leave off. I will see you guys on Monday, and we will hopefully wrap up a few factors and do some example problems.